and welcome back. In this lecture I'm going to show you how to use the EasyDriver breakout with a NEMA17 stepper motor. Let's have a look at the two components. The EasyDriver is a small PCB which is very popular for driving stepper motors. It can be used with a variety of stepper motors, either 2-phase or 4-phase. Outputs are quite a bit of power, so 750 milliamps per phase. So if you are using a 2-phase stepper motor, that would be 750 milliamps for each individual phase. Now, one EasyDriver breakout can drive two phase motors. So if you have a setup where you've got, say, 2 times 2 phase motors, you're going to need 2 of those EasyDrivers. Another nice feature that the breakout has is called microstepping, MS. So you can see there's a couple of pins on this board called MS1 and MS2, and what you can do with those is to use it to finely calibrate the stepping motion of the motors. So if, for example, a stepper motor has a step at 1.8 degrees, then you can configure microstepping so that you can divide that, say, to 8 or by 8, and therefore you can have a much finer control of the motion of your stepper motor. The breakout contains a Allegro A3967 driver chip. It's also open source, so you can go to this website and download the schematics for the PCB, so you can create your own if you want to, or you can customize it to fit your particular requirements. And it also comes with a really nice library, which we'll be using in the demo later on. The library is called Axle Stepper, very easy to use. Supports many different types of stepper motors, as I'm going to show you a bit later on during the demo. It's also non-blocking, which means that you can set the speed and direction and final position of the motor, and then let the controller take care of getting the stepper motor to that position at that speed, while your Arduino is off doing other things, perhaps communicating with other devices. So that's called non-blocking. And finally, if you have a project that requires multiple stepper motors to be working at the same time, then Axle Stepper can support that. So it can support multiple motors running at the same time. In the demo, I'll be using the NEMA17 stepper motor. It looks like this. It's got a 1.8 degree step, which is typical for motors of this category. This particular one is a hybrid stepper motor, which means that it's using technology so that in a relatively small package and for a small price, you get quite a bit of power packed in it and fairly good features. So the particular one that I'm using can support 4 kilograms of holding torque, which is a pretty good specification. Finally, motors like that you find in places like 3D printers and robots and things of that sort. Here's a circuit already connected. I'm going to walk you through what these connections are and then plug it in and get it to work. So starting with the Arduino, just 3 wires are needed for this setup. I've got the common ground, so that's on the ground pin, goes to the 3rd pin of the EasyDriver, and then these two, the blue and the white, control the motion. So the blue one is connected to pin number 9. Of course, you can change that in the sketch, but it controls the speed. So every time that digital pin 9 goes too high, it causes the motor to move by 1.8 degrees. The direction of the move is controlled by the white wire, which I've got connected to pin number 8. And again, that is configurable in the sketch. So when the pin number 8 is high, the shaft is going to move one direction, and when it's low, it's going to move the opposite direction. That's about it on the Arduino side. On the EasyDriver side, you provide power through these two pins as ground and positive. I've got the EasyDriver connected to a 12-volt power supply, which is actually supplying 15 volts for some reason, probably low quality. Doesn't really matter. The EasyDriver can receive power up to 30 volts or thereabouts. I did a mistake earlier with my polarities, and you can see I burnt the plastic here. Oh well. Good news is that I didn't fry the EasyDriver, so they're pretty tolerant to mistakes like that. Finally, you've got the phase connections. So you got two pins for each one of the two phases of my motor. Now, as I said in my previous stepper motor lecture, usually these motors don't come with clear documentation about which wires correspond to which phases. So very often this is something that you've got to do yourself. So just to show you what the easiest way to do that, I'll unplug these two wires which already know that belong to the same phase, and show you how I do it. The two wires for that come at either end of each phase, when you use the continuity tool, you'll see that my multimeter detects that there is continuity, or alternatively you could use the resistance meter to check that these two wires, which make up a single phase, have got a very low resistance, about say 3 ohms. Right, so that's how you know that two wires belong to the same phase. Now, if instead of these two I had measured, say, these two, which of course now I know that they belong to different phases, but you can see that if I try the ohm meter, resistance is I almost said futile, but resistance is very high. So that tells me that these two wires are not part of the same phase. Right, so use your multimeter to figure these things out. Now the way that I've connected these wires here is not very good, I admit. So you just need to be careful not to short them. Okay, back to normal. Alright, now let's have a look at the sketch. You can use the EasyDriver without a dedicated driver library. You don't need Axel Step to test it out. So let's have a look at the bare demo. So what I'm doing here is extremely simple. Can't get any simpler than this. I use my two pins, so 8 and 9. Both of them are going to be output, and I start them at low. And then inside the loop, I simply send via pin 9, I send pulses, high pulses. Every time we've got a high pulse sent over, the shaft will advance by 1.8 degrees. Show you how I can change the direction as well. Let's plug it in first. Okay, I'm still running the earlier sketch I was playing around with, so I'll upload that. Okay, so single direction just moves forever. What if I want to, what happens if I increase the delay for the high? Actually, I'll increase the delay for both. There you go. So it's slower. So the more delay you put in between pulses, I'll make that 100, the slower the shaft moves. There you go, very slow now. So the idea here is that the EasyDriver is
simple enough to use without a library if you have a simple application that you're building. Okay, what about direction? Maybe let's do this. I'm going to add a couple of lines, and say here I'm going to change direction by going to pin 8 and writing a hi to it, and then I'm going to repeat this, let's say 100 times. Declare my, actually no, I don't need to do that. So for inti equals 0, I less than, I'll make that 200, right? So 200, and then I plus plus, right. Okay, format that. Right, and of course I need to do the same thing up here. So I say, just going to copy this part, put it up here, close, and I also need to change the direction, make that low. So what's going to happen now is that the motor is going to move 200 times 1.8 degrees in one direction, and then it's going to move 200 times times 1.8 degrees the opposite direction. Okay, there you go. If I increase that to 400, I shouldn't say degrees, I should say steps instead. Okay, so 400 steps each direction, and so on. Okay, so that's how you can control your motors without the axle stepper library. Well, let's have a look at the axle stepper library anyway, because it gives you some additional nice features without much work on your behalf. So here's a little sketch I want to play with at the moment. So we start by including the library and then initializing the stepper object. So number one means number one describes a type of motor that I want to use, and there is documentation about this. Of course, if you go to the axle stepper documentation, you'll see the types of motors that the library supports, and I'm just using the simple case here, just a simple driver. So I want to implement. Next, starting with describing a position. So this is just a number that describes how far the motor is going to spin. Right, it's just a number, just an integer. Now in the setup, I can do things such as set maximum speed, and again, that's a number that describes how quickly the shaft is going to move, but it's just arbitrary, so the speed is going to be different between motors. So in my case, 8,000 means a particular degree movement per second. We'll have a look at that in a second. So you need to experiment with those numbers to find the ones that match best your purposes, your application. And you can also control the acceleration. Inside the loop, you what this is going to do is it's going to rotate the shaft until it reaches a position 5,000, and once it reaches that position, you can test that by checking the distance to go function, then wait for a little bit, about half a second, and then alternate the direction of travel and get the stepper to go to position number 5000, traveling the opposite direction. Once you say run, then your program can go and do other things, and the controller is going to make sure that the stepper motor eventually reaches that position. So let's upload it. Okay, so going to 5000 position, and then turning around opposite direction and going back to position 5000 again. If I play with those numbers, let's say make the acceleration a little bit slower, so make that 500. Whoops, 500. Upload again. Okay, it's going to do the same thing. It's going to cover the same distance, but at a smaller pace. If I make the 8000, I'll make it 4000 maximum speed. Ooh. Not responding. Try again. There you go. Okay, so it's now traveling at a lower speed. Other interesting things that you can do with this library, let's see, run speed and maximum and speed and acceleration. You can set the speed inside your sketch. So for example, I could say here step set speed. I'll make it 5000. And this way you are able to change the speed at any part of your application, regardless of what the original speed was set in the setup. You can check the current position if you need to, so this is going to return a number that represents the current position of the shaft. So that's about it. Just lastly, before I finish this lecture, there's a couple of pins here. There's MS1 and MS2 on the other side of the board, and these two pins allow you to enable micro stepping. So they provide you the ability to fine tune and fine control the positioning of the shaft. There are sketches, example sketches that come with the library that show you how to use these two pins. That's all for now. As always, if you have any questions or comments, please don't hesitate to reach out.